In this segment, we are going to talk about the de Broglie relationships. So what are the de Broglie relationships? So let's recall the quantum relationships that we discussed in the previous few lectures. So for a photon, its energy, E, is given by h bar omega, where h bar is a rationalized Planck's constant. So it's Planck's constant divided by 2 pi, and omega is related to the frequency nu through this relationship. So omega is what we call angular frequency. But in the previous segment, we also discussed a relationship between the momentum of a photon and its wave number. And that relationship was the modulus of the momentum of the photon is given by h bar k, where k is the wave number. So these are relationships which are valid quantum mechanically for the photon. What de Broglie proposed was that if light has a corpuscular or particle-like nature, why wouldn't, say, particles or matter have a kind of wave nature? So de Broglie proposed that these relationships should also hold for matter. So the de Broglie relationship is that these So de Broglie proposed this relationship from a kind of a deep-seated sense of symmetry, that nature should be symmetric. And when he guessed it, there was really very little evidence that this was true. But after he had proposed it, experimental evidence was found, and of course de Broglie got the Nobel Prize for it. So, let's discuss some of the consequences of this. So, for example, if you have a particle, if the particle, say, is non-relativistic, then we expect the energy to have a component which is going to be, they say, the kinetic energy, and a component which is the potential energy. Now, if I use the de Broglie relationship, then what I'll have is that I can derive a relationship like this. On the left-hand side, I get h bar omega. On the right-hand side, I will get h bar squared k squared by 2m plus v. So this is an interesting relationship because why? Because if we're dealing with waves, a wave will have some wave vector, which would be a 3 vector, and its modulus would be given by this k, and the wave would have some wavelength, and there'll be some speed. Let's call that speed, say, small v, and therefore the frequency is going to be given by lambda times the frequency. The speed is going to be given by lambda times the frequency. And we can write this as lambda by, say, 2 pi times 2 pi nu, and therefore the speed of the wave is going to be given by, say, omega by k, right? So we see that there's going to be some relationship between the wave vector k and its magnitude, the frequency omega, and the speed, and these two guys, in addition to satisfying this relationship, will also have to satisfy this relationship. So this was a kind of challenge that any fundamental theory of quantum mechanics which incorporated in it a wave nature of particle should be able to describe this energy, this relationship between the frequency, angular frequency, and the wave vector of the wave. And in a conference, this was pointed out as a challenge, and Schrödinger took up the challenge and he came up with an equation which successfully gave rise to this equation.